Everybody, in this video we're going to talk about the pH scale. We're going to calculate the pH of some strong acids. We're going to spend a little bit of time talking about the kind of the origins of where the pH scale comes from. So in this case, let's get started. The pH scale is kind of a pretty cool thing. There's, believe it or not, a lot of related math and chemistry that kind of intertwine with each other. So let's really take a minute and look at what's going on. Okay, now pH is defined as the negative log of the concentration of the hydronium ion. This describes a base, okay, or sorry, an acid. Okay, an acid is an acid because it produces hydronium ion when it's dissolved in water. So pH, I don't know exactly where the phrase pH comes from, but I always think that pH means per hydronium ion or per hydrogen ion. I don't know if that's exactly true. My high school chemistry teacher taught me that once, but it is what it is. So anyways, pH is basically, it tells us about what an acid is. I don't know where my thing went here. There it is. Okay, so now one thing that I want to make sure that is very clear before we kind of move on is that when you have the pH of the pH doesn't necessarily tell you about the strength of an acid. It does tell you about how potent it is or about how dangerous it is, but the strength of an acid is kind of solely based on whether it dissociates, how much the acid dissolves or dissociates in solution. Okay, and so it's possible for an acid that we would call weak to have a pH of 0.5. And it's very possible also for us to have a acid that we would consider strong to have a pH of 6. Okay, so I just want to make that clear, is that the strength of an acid, a strong acid, is only defined as something that completely dissociates in water. Okay, so this is the formula for pH. Let me get rid of some of this junk that's around here now. Okay, and I think it's important mathematically for us to understand how pH kind of works. Okay, so for strong acids and bases, okay, or for strong acids, the acid completely dissociates. So that means that if we have HCl and we have a 0.1 molar solution of HCl, hydrochloric acid, that means that when HCl reacts with water, this completely dissociates. It's not in equilibrium. Completely dissociates to form H3O plus Cl minus. So this means if we had 0.1 molar here at the beginning, how much H3O is produced? Well, all of this dissociates, so at the end we're going to have none, but here we're going to have 0.1 molar. So what ends up happening is that, what ends up happening is that strong acids the concentration of H3O plus is equal to whatever the concentration of that strong acid is. And I think that's important. Okay. Now weak acids, all bets are off because it doesn't completely dissociate. Weak acids, it's an equilibrium, and that's where we're going to be going. But for now, let's talk about strong acids. Okay. Now, let me take a minute and let's try to let's actually calculate the pH of an acid. Let's say that you have 0.003 molar H2SO4. Okay. Now, H2SO4 is an interesting acid because notice it has 2 protons. But here's what I'm going to tell you, and this is why I picked this example, is that in this case, for this, it's only the first proton that is strong. So when H2SO4 comes in contact with water, one proton leaves, leaving behind a hydrogen sulfate ion. Okay, so only one proton is strong. So our statement that the concentration of the H3O plus equals the concentration of the acid still holds even for H2SO4. Okay, and so what this tells us is that in this case, let me move this down a little bit. So what this tells us is, I'll do this in a different color, ICE. And in this case, this is a stoichiometric ICE chart, meaning that this is the end of the reaction. But since this is 0.003, we're going to have 0 at the end. And so this, we're starting off with about nothing. And at the end, because this is going to lose that much, this is going to gain 0.003. It's a 1-to-1 stoichiometric ratio. Okay, this is a weak acid. Okay, that's not a strong acid. So, having said that, now let's move down. Okay, so now let's calculate the pH. Real straightforward. It's really just a plug and chug. And so pH equals the negative log of the concentration of the hydronium ion. So the negative log of 0.003. Okay? And just be careful when you type this in your calculator. This is why I want you to use a calculator that you're familiar with. And so negative log 0.003, I do that, and you get a pH of 2.52. Okay? And that's your pH. Okay? Now, let's go backwards because I think it's important to go over the math a little bit. Okay? Let's say we have an acid, let's say we have HBr with a pH equal to 5.3 units. pH doesn't have any units, but that's what we can do. So now what we want to do is we want to find the concentration. So what is the concentration of HBr? Now, HBr is a strong acid, so that means that the concentration of HBr is going to equal the concentration of H3O plus Okay, and so let me do my work in a little different color here. Great, I added this, so I'll put that right over this. H3O plus, okay? And so again, we're going to use the same formula. It's a strong acid, so it's pH equals negative log of the concentration of the hydronium ion. But now, when we plug and chug, we go 5.3 equals the negative log of the concentration of the hydronium ion. And so now we need to, and this is not proper math terms, but I'm going to say d-log this. Okay, we have to figure out how this is going to get us only this. Okay, so the first thing that we're going to do is we're going to, divide by -1 to get rid of this. So we get negative 5.3 equals the log of the concentration of the hydronium ion. And then the next thing we're going to do is we're going to now d-log this. In order to get rid of log, you raise this term, you use that as the power of 10. And so if you do it to one side, high school algebra, you have to do it to the other side. It may even be before high school algebra. Okay? And so what this does is this completely gets rid of this. Okay? And so by doing that, we get 10 to the negative 5.3 equal. Whoa, let me just really quick. Looks like I'm having a little bit of an issue here. So 10 to the negative 5.3 equals the concentration of the hydronium ion, which in turn equals the concentration of HBr. Okay? So now we'll do 10 to the negative 5.3. Okay? And so that is 5.01 times 10 to the minus 6 equals the concentration of H3O plus, which again equals HBr. And now this is concentration, so this is in molar. Make sure you get your units down right. Okay, and so that's how we use the pH scale to calculate, or this is how we use the pH formula to calculate the pH of strong acids and strong bases.